9-6, which we're going to take a second to go over and finish up right now. So hopefully you took a look at that whole section. And so I'm going to just label this 9.4. Hopefully you looked at that section and figured out a lot of these different things right here. So we're going to buzz through. Were there any in particular that you had questions on? Or did the section pretty much make sense? I know there's a couple that maybe didn't, and we'll definitely look at those. But did you read it, and did it make sense for the most part? Brandon, how about you? Did you do the homework? All right. Okay, any questions? Okay, I want to take a look at a couple of things then. So we talked about this fundamental counting principle that if you've got a couple of choices to make, you just figure out how many choices you have for the first one, how many choices you have for the second one, the third one, and so forth, and you just multiply them all together. But the idea of a permutation and a combination are really important. So when we do a permutation, the thing you've got to remember is order matters. Order makes a huge difference when we're doing a permutation. Okay? And we use factorials to figure out permutations quite a bit. It says how many different permutations are there between the letters A, B, C, D, and F. So there are 6 of them here. So if we were to take all 6 of those and just put those in some order, the order A, B, C, D, E, and F is a different order than if I did A, B, C, D, F, and E. Okay? That's different, and it counts as a different arrangement. Okay? So when we permute things, we reorganize them and we rearrange them. So order makes a huge difference when we're talking about permutations. Okay? So a classic example of this, and I've got another one toward the end, is if you were in a horse race or any type of race, okay, it matters what order you finish. Okay? So if we've got these horses, and we'll call them Bob, Sally, and Jane, okay? If you're the owner of the horse named Bob, it's a big deal whether Bob comes in first or third, okay? It's not just enough to place or finish the race. It's a huge difference what place you come in, okay? And that's why order makes a difference. So even if these 3 come in 1, 2, and 3, and then we run the race again and it comes in 1, 2, and 3 this way, huge difference as far as the outcome is concerned. Okay, so order is a huge difference, and we call that a permutation. Okay, so with the same group of horses or individuals or choices, permutations, there are tons of permutations as opposed to just putting them in a group and saying, oh, they all finished. It doesn't matter what order they were in. Okay, all right. So there's a formula for permutations, and it looks like this right here. Okay, it's a pretty easy formula once you get used to working with it, and I would advise doing a lot of these by hand and getting used to canceling things off and stuff like that. So the permutations are just n factorial over n minus 1 factorial, and that's the number of permutations of n objects taken r at a time. So if I did something like this, let's say I have 10 horses in the race, and I just want to know how many different combinations are there for them to finish first, second, and third. Okay, well, the short way to figure this out is to just say, well, how many choices are there for first place? 10. This is kind of like without replacement. Once that one horse finishes first, how many choices are there for the second one? There are 9, and then there are 8. So the answer on this would be 720. Okay, the formula gives you exactly the same answer, but it's important to think about why it works that way. So this would be 10 factorial on the top, and then 10 minus 3 factorial on the bottom. Whoops, I'm thinking ahead. 10 minus 3 factorial here. So this is 10 factorial over 7 factorial. And this is what I think would be a good exercise. If you have 10 factorial over 7 factorial, what you have here is 10 times 9 times 8 times 7 times 6 and so forth, all the way down to 1. And then you have 7 times 6 times 5 times 4, all the way down to 1. I can cancel all of those with all of those, and that's why the 10, the 9, and the 8 are left. Does that make sense? Okay, let me show you one other way to think of it that in the long run is helpful. Think of this as, if you know the bottom is 7 factorial, let's write this as 10 times 9 times 8 times 7 factorial. Instead of writing all of those, just realize that's where we're going to start canceling things off. Okay? So if I were to write this down in general, watch please, I'd have n times n minus 1 times n minus 2, all the way down to n minus r factorial, and the bottom would be n minus r factorial. Then I can cancel those off. Okay? Seems very silly. If we got the answer this quickly, why would you bother writing it down all of these other ways and thinking about it all of these other ways? It's because in the long run, that way of thinking is going to come in really handy. Okay? So if you do a little bit of practice with it now, when you see it later on in like a calculus class or something, you'll be in better shape. Okay? So then they went through, if we've got some permutations where we've got some repeats, where we've got repeated objects, it's just going to be n factorial over however many repeats there are of that first one, however many repeats there are of the second one, and the third one, and so forth. So the example that they gave here was, we're going to rearrange the letters in banana. Okay, now there are 1, 2, 3, 4, 5, 6 letters in banana, but I can't tell the difference between that N and that N and that A, and that A. So we've got N's repeated twice and A's repeated 3 times. So we would do 6 factorial over, we just divide it by the repeats. So 2 factorials for the N, 3 factorial for the A's. Cancel there. Cancel here. 3 times 5 times 2. Answer 60, just like they came up with in the book. Okay? Yeah.
So does that mean you're saying that that's getting rid of all the duplicates, like, so that this same word can't be written twice just because there's like 2 ends?
Yeah, like we wouldn't, so if we take the word banana, and let me label this N1 and this N2. So if I do it like that, and then I rearrange it and I spell it like this, I'm counting those as exactly the same arrangement in the same word, because you can't tell, without putting something extra on there like I did with the subscript, you can't tell the difference between the two of them. Okay, so those are what they call the distinguishable permutations. Okay, we can't distinguish between the two of these without that subscript. Does that make sense? Okay. Any questions? Okay. So on the last page, they had a couple of problems, and then I added this one. Okay, these are called combinations, and combinations are different than permutations, even though the formula looks fairly similar. So in a combination, this is the big deal here, order doesn't matter. In the horse race, if there was a prize attached to first, second, and third, it's a big deal whether or not you finish first or finish third. Okay? But what if it's like some of the trials in the Olympics where as long as you finished in the top 3, you're going on to the next round? Does it matter whether you finish first, second, or third? In fact, if you watch some of those, there are some of those skaters and people like that, as long as they're finishing second or third, they won't even try very hard because they're storing things up. Okay? The time doesn't carry over or anything like that. They just want to make sure they get in. Okay? So if the order doesn't matter, then we're talking a combination. So if I go back to this example right here, okay, if I've got Bob, Sally, and Jane finishing first, second, and third, or third, second, and first, aren't those the same qualifiers either way? So does the order that they finished make a difference? Not at all. So there are fewer, even just with that one, instead of counting that as two different finishes, we'd count that as one finish. So there are fewer combinations than there are permutations. Okay, let me say that again. There are fewer combinations than there are permutations, and we can see that in the formula. Take a look at the formula. This right here, let me blow this up just a little bit. That right there, that's the number of permutations. And then we've got this other thing that we're dividing by. We're going to divide by r factorial. Since we're dividing by a bigger number, that's going to make the overall number of results smaller. Okay? So, let's see. In how many different ways can three letters be chosen from the letters A through E? We're just going to choose the letters. It doesn't matter what order they're in. Okay? We're just going to put them in a group. Okay? So according to this, this would be the formula for the number of combinations of 5 things taken 3 at a time. So we'd have a 5 factorial on the top, a 5 minus 3 factorial on the bottom, and a 3 factorial on the bottom. Okay? And if you followed along and did any of these, you notice that this works out the same way every single time. The top is going to be a factorial. And on the bottom, I'm going to have, in this case, a 2 factorial and a 3 factorial. These will always add up to this right here. So if I had a 7 factorial on the top, the two numbers on the bottom would have to add up to 7. So I could have a 4 and a 3, a 5 and a 2, a 6 and a 1. Does that make sense? So I'm going to cancel off 5, 4, 3 factorial. Let me get rid of that. There's a 3 factorial and a 2 factorial. Those are going to cancel. That's really a 2 times 1, so I'm going to cancel here. So I end up with 10. Again, it might seem silly to go through this, okay? And probably next week I'll show you how to do this on your calculator, okay? But going through and canceling things off is actually a good one, okay? Now, without looking at your book, okay, or what you've got in your notes, think about how you do this one right here. 52 cards in a deck, and it says poker hand consists of 5 cards dealt from a 52 card deck. How many different poker hands are possible? So think about when you play cards. Does it matter what order you put them in your hand? If you take them in your hand and you rearrange them, don't you still have the same hand? So does order matter? Doesn't make a hill of beans difference. Is this a combination or a permutation? Combination, okay? So we're going to do the number of combinations of how many things? 52 things taken how many at a time? Taken 5 at a time. So that means I'm going to have 52 factorial over 47 factorial and 5 factorial. Now, even though we do a ton of canceling here, this is going to be 52, 51, 50, 49, 48, and I'm going to write 47 factorial. 47 factorial, 5, 4, 3, 2, and 1. Cancel those off. And then I'm going to cancel some other stuff. These two make an 8. That would go in 6 times. Cancel this with that. That would be a 2. And the only other thing I can cancel would be a 5. It'll cancel with this, and that'll be a 10. So if I did 52 times 51 times 10 times 49 times 2, that'll give me the answer. Okay? And from your book or from your calculator, if you've plugged that in, it's a surprising number of hands, isn't it? How many hands are possible? 2.5 million. 2.5 million different poker hands are possible if you're playing 5-card poker. Okay? Any questions? Okay. The last problem in the section I would expect you to have a little bit of trouble with. We did skip 9.5. We're going to go back and we're going to do that next week. I wanted to talk to you about counting techniques, permutations, and combinations. before we did that. Let me just run through this one right here. It says find the total number of subsets that a set of 10 of a set that has 10 elements. Okay, that may have seemed a little bit confusing. The notation for something like this can be written like that. Instead of saying the number of combinations of 52 things taken 5 at a time, you can say this: 52 choose 5. 52 choose 5 is the way that's referred to. And it means the same thing. So both of these are equivalent. The answer to this would be 2.5 million, just like the answer to that is 2.5 million. Okay? So find the total number of subsets of 10 things. Doesn't matter how many you take. Every possible subset. So the first thing we'd do is we'd do 10 of them, and we wouldn't take any of them. Let's think of them as cards. If you've got 10 cards sitting there, how many different ways can you take none of them? One. You have to leave them all on the table, right? There's only one way to do that, okay? So let's see if this formula works. This would be 10 factorial over 0 factorial and 10 factorial. Okay, remember what 0 factorial is? 0 factorial is 1. 10 factorial over 10 factorial, I get one answer. One way to do that. Okay, now that's not the only subset. I could do 10 of them and take them one at a time. 10 choose 1. Now stop and think about that for just a second. We got 10 cards laying on the table. I'm going to take them one at a time. How many different ways can I do that? 10 times. 10 different ways, right? I can choose the first card, put it back. Choose the second card, put it back. So there would be 10 of those. So we expect the answer to work out to be 10. So this is 10 factorial over 10 minus 1 factorial. So that's going to be 9 factorial and 1 factorial. Remember, these are always going to add up to be that. So this is 10 times 9 factorial, 9 factorial, 1 factorial. Those cancel. 10 over 1, 10. Whoops, 10. So I'm going to keep going and I'm going to do this. I could take them 2 at a time. Cancel here. 5. I get 45. Okay. When do I stop this? Well, I only have 10 cards. So I started by taking none of them. Then I started taking them one at a time. Then 2 at a time. 3 at a time. So I do 10 choose 3. Then I do 4 at a time. 5 at a time. 6 at a time. Whoops, I have a tendency to write these as fractions. I don't know why. I always have. Okay? When would I stop? If I've got 10 cards on there, how many are there? How many different ways are there to take them all 10 at a time? There's only one way to do that. I gather them up. I've got them all. There's no other way to do that. Okay, the order that they're in my hand doesn't make any difference. So this would be 10 factorial, 0 factorial, 10 factorial. Those are going to cancel off. They're going to be a 1. You'd find every one of those. By the way, how many different answers do I have to find? What is it? 11. 0, 1, 2, 3. Start at 0, go to 10. That's 11. Okay? You get those 11 numbers and you add them up. Okay? All right. Okay, let's take a look at the last one. Again, I just want to illustrate the difference between the two of these. So permutations, the way we write permutations is n choose r, and there are usually tons of permutations. There are always more permutations with the same numbers than there are combinations with the same numbers. Combinations are written this way, or they're written this way. Okay? And the formula here is just n factorial over n minus r factorial. The formula here is n factorial, n minus r factorial, times r factorial. And again, do some practice, cancel some things out and stuff like that. Make sure you can do that. That's really good practice. But here is a classic way to do this, okay? To illustrate the difference between a combination and a permutation. So I've got two problems here. There are 15 people in this classroom. Let's say we elected a class presidency. A president, a vice president, and a secretary. So of the 15 people, we're going to take 3 of them and make them into a class presidency, okay? Now, if we chose Cameron and Brandon and Nathan to be in that class presidency, does it make a difference in which office they serve? Yeah, so aren't there a bunch of different ways to take those guys and have one be a president, one be a vice, and then rearrange them, right? So the same 3 people is going to make a different arrangement. There are going to be more options there, even with the same 3 people, right? Combination or permutation? Permutation, because the order we choose them makes a difference, just like the order that they finish a race is. So this would be the number of permutations of 15 people taken 3 at a time. 15 factorial. You can think of the formula, but the denominator is going to be 12 factorial, n minus r factorial. The 12 factorial is going to cancel off, and I'm going to be left with a 15, a 14, and a 13. So if I multiply those together, just with the 15 people in this classroom, how many different class presidencies are possible? Tons, right? Isn't it like 2,500-ish? 2,730 different possible class presidencies just with the people in this classroom. Okay, now let's change the scenario just a little bit, and let's say they're going to form a 3-member committee with no ranking members. Nobody's in charge of the committee. We just put them on a committee so they can make some decisions. So let's take the same 3 people, Brandon and Nathan and Cameron. Does it matter what order they serve on the committee? You can rearrange them on the table all you want. They're still the same committee, aren't they? So does the order make a difference? If the order doesn't make a difference, then this is a combination. So this is going to be 15, choose 3, 15 factorial. We are going to have a 12 factorial, but we're also going to have that 3 factorial, so they add up. So this is going to be 15, 14, 13, 12 factorial. There's our 12 factorial. And here's why we have fewer number of permutations than, combinations than permutations, because we're going to end up dividing by this extra thing right there. That's going to go away. This is going to be a 3 and a 2. So I'm going to make that a 5, and I'm going to make that a 7. So I have 35 times 13. And what is 35 times 13? 910? So way fewer combinations than there are permutations. Okay, any questions? Okay, please practice the notations. Please be done with 9.4 and 9.6. We'll correct those at the beginning of the class on Monday. And then we're going to do 9.5. When is the test scheduled? Next Thursday. Next Thursday. So we'll take a day or two to cover 9.5, then we'll review, take the test next Thursday.